In this session, we will introduce the first law of thermodynamics. So let's consider an experiment in which a gas is enclosed in a cylinder fitted with a frictionless piston. The bottom part of the cylinder is made up of a diathermic wall. So this is the bottom part. This is diathermic, and hence it permits the flow of heat, diathermic, and all other sides of the cylinder are adiabatic, including the piston. So as shown in the figure here, the gas is in thermal contact with a flame which is at a higher temperature. So the flame is at a higher temperature, hence heat can enter the system. At the same time, the gas is compressed by the piston, means some work is done on the system. Gas is compressed, so the arrow shows the piston to be moving down, means work is done on the system simultaneously. Now since we permit the flow of heat into the system during the compression of the piston or during the work being done on the system, you can see the work here is not adiabatic. Instead, it is a diathermic work. The reason is well and clear. We do the work on the system not under adiabatic conditions. Instead, it is under diathermic conditions. So the work done here is not adiabatic. Instead, it is a diathermic work. Now, if you focus upon the internal energy of the system here, that is a gas, the internal energy changes in two different ways here. So the internal energy changes in two ways in this experiment. What are they? First one, it's by flow of heat, or by allowing heat to flow. By allowing heat to flow, let's say in this example, into the system. By allowing heat to flow into the system, certainly the internal energy of these gas molecules will be getting changed. And one more thing we are permitting, we are making the piston move. So by doing work, in my example it is on the system because I am compressing it, by doing work on the system. So as a result of both of these simultaneous process, the internal energy of the system will change, or I can say the state of the system changes from one to another. So let's say, let Ui be the initial internal energy of the system. Initial internal energy of the system. Initial internal energy of the system, let's say. Okay. Now, if the amount of heat that flows into the system, if the amount of heat that flows into the system be Q, let me say Q is the amount of heat that flows into the system through the diathermal wall here, then the internal energy of the gas will increase to, is it not? If Q is the heat entering the system, we are following a sign convention for heat also here. heat entering the system will be taken as positive. That is the convention that we are following here. Then what will be the internal energy? The internal energy will be increased. Already there is an initial energy Ui. With that, I have to add the heat that has entered to the system. Now, if we consider W be the work done on the system. So, if I'm doing in two steps, we can consider it simultaneously too. If W is the work, I told you this is the diathermic work done on the system, and as per our established sign convention, work done on the system is also taken as positive. It will also cause an increase in the internal energy. Then the internal energy further increases. Can consider this one in a two-step manner. So what will be the thing? That will be, I can say, internal energy becomes UF. Let me say that is the final internal energy. That will be equal to Ui, which was the internal energy to begin with, plus the heat that has flown into the system, Q, plus the work, diathermal work. Let me write diathermal work that has been done on the system. Now you can rewrite this equation as UF minus Ui, which is nothing but a change in internal energy of the system. That is equal to simply Q plus W. And let me specify this W is diathermic. Q plus W. So this equation is usually considered as the mathematical form of first law of thermodynamics. First law of thermodynamics can be represented in different ways. This is the most common way of representing the first law of thermodynamics, or this is the mathematical representation of the first law of thermodynamics. Okay, so the first law of thermodynamics can be mathematically stated as like this: the change in internal energy of the system, that is change in internal energy of a system comma, I am representing it as delta U, that is nothing but U final minus U initial, that is equal to the sum of the heat that enters to the system and the work that is done on the system, Q plus W, where we understand that this W in this equation represents the diathermal work. This is the mathematical form of the first law of thermodynamics. Now, if you want, we can rewrite this equation as, we can write what is Q equal to. So therefore I am rewriting this one as Q equal to, I already have UF minus Ui, so minus this W. Remember, this W is diathermic, and this equation can be used to provide a thermodynamic definition of heat. So equation can be used to define heat. The concept of heat, or this quantity heat, can be defined thermodynamically. So heat can be defined precisely or thermodynamically using the equation. what is given here. So how do we define that quantity? You can see this is the definition that you can use. Earlier we defined heat as something which flows due to temperature difference between a system and a surrounding. Okay, now we are having a very precise definition of heat in terms of the change in internal energy of the system. Let's see how it is defined. So the statement is given here: when a closed system differ in temperature. So take care of this some terms here. The condition is that the system should be differing in temperature. So when a closed system differ in temperature from its surrounding, undergoes a change of state. So it is changing from the initial to the final state due to the performance of diathermic work. So that is what is shown here in this equation, due to the performance of diathermic work. Remember, it is not adiabatic, it is diathermic work. Then the energy transferred, hope you remember, heat was defined as energy in transit or motion by non-mechanical means. Means you should not consider energy transfer that causes due to work. It is non-mechanical means. Due to the difference between change in the internal energy and the diathermic work, which is equal to the difference between change in internal energy. This is change in internal energy, delta U, and this is W dia. And so the difference between these two under this given condition is what is called heat. So I can say this is a numerical or a thermodynamical definition of the heat. So when a closed system differ in temperature from its surrounding and it undergoes a change of state due to the performance of diathermic work alone, then energy transferred by non-mechanical means is equal to the difference between change in internal energy and the diathermic work, and is known as heat. So that is the thermodynamical definition of heat. Remember, that is the definition of heat using the first law of thermodynamics. So to conclude this one, this is the way in which you understand the internal energy of a system can be changed in two ways. That is the essence of our law. Internal energy of a system can be changed in two ways. One is by doing work on the system or by the system, and the other one is by transfer of energy by non-mechanical means. And transfer of energy by non-mechanical means is what is known as what? Heat. So the internal energy can be changed by either work or by heat. Okay, and this thing actually is nothing but a restatement of the law of conservation of energy. The total energy of the system is related to the work done and also the heat transferred. So by using proper sign conventions, we will be able to make sure that this law always gives you the law of conservation of energy. So to conclude, we can say that the first law of thermodynamics contains three related ideas. We have got three very important or related ideas. First of all, the law defines or it predicts the existence of an internal energy function. Already we have seen that internal energy can be regarded as a function, thermodynamic function. Okay, so it verifies the existence of a function which depends on the initial and final states of the system, and that function is what is known as the internal energy function. And remember, this internal energy function U can be represented as a function of the thermodynamic variables. Say for example, I can say pressure and temperature. I can write it is a function of pressure and temperature, and also I have freedom to write as a function of the volume and temperature. And you can see that there are actually three variables, and I am writing this function in terms of only two variables. The reason is that the other one automatically gets fixed due to the equation of state. So U can be written as a function of P and T. It depends on what parameters we are actually measuring. in what parameters we are interested in. So if this is the case, you know what will be the differential of u, etc. So differential of u will be written in what way? It will be written as dou u by dou p is not into dt, sorry, into dp plus what will be the next thing? Dou u with respect to dou t into dt. So that is the way in which you write this one. Of course, you know that in the first partial derivative, temperature is kept a constant, and the second partial derivative, pressure is kept a constant. If you write this internal energy function in terms of volume and temperature, then it will give you a differential du will be written. How do you write du? Just recall that the partial derivative defines that dou u with respect to dou v, keeping temperature as a constant, into dV. I'm not writing the constant here, plus dou u with respect to dou t into dt. Here volume is kept a constant. You can see in both the cases I have included temperature here because temperature is of paramount importance in thermodynamics. So that is first thing. So existence of an internal energy function is given by the first law of thermodynamics. Second one is that it is nothing but a restatement of the principle of conservation of energy. You know that the total energy given to the system is always conserved. That is what is shown by equation of the first law of thermodynamics. And the third related idea is that heat is considered as energy in transit. Heat is considered as energy in transit by virtue of due to which factor? The temperature difference. So that is why we can say that the first law of thermodynamics actually is used to define the quantity heat mathematically or thermodynamically. So these are the three related ideas that is contained in the first law of thermodynamics. Now let me recap the sign conventions that is used for heat and work. Already this is the see, this is our just first law of thermodynamics. We will be using this form of first law of thermodynamics. Delta U is equal to, if I am taking a finite thermodynamic process, then the change in internal energy can be caused in two different ways. Okay, one is due to the heat and other is due to work. Now heat may flow into the system or it may flow out of the system. Work may be done on the system or work may be done by the system. So accordingly there will be a change, either an increase in the internal energy or a decrease in the internal energy. Now you know that there can be four different possible combinations of the two variables on the right side. Okay, what are they? They are actually shown in the four diagrams here. So you consider the first diagram over here. So it's a figure number 1 here. In figure number 1 you can see that there is a flame here, there is a source here, a source of heat here. Of course the temperature here will be greater, and the bottom part of the cylinder has been shown as a diathermic one. Okay, so heat can flow into the system. So in the first diagram, Q is entering the system. Clear to you? And you can see what is the direction of the piston movement shown here. So the piston is shown to be moving upward in the diagram. Means it is undergoing, system is undergoing expansion. Hence, you know, the work is done by the system. So work is done by the system, and as per our accepted convention, work done should be taken as negative. So W is negative. Negative is shown as less than 0. Okay, 0, negative, positive. Okay, so W is shown to be negative, that is less than 0. This side it is 0, this side it is more, you know. Okay, what about Q? Since Q is entering the system, you know, it will cause an increase in the internal energy of the system. Okay, so Q is taken to be positive. Q is taken as positive, right? Now in the second diagram you can see Q still heat is entering the system, so of course Q is positive, right? And what happens to the piston? Piston is moving down, means somebody is doing work on the system. So this work done on the system by some external agency will cause an increase in the internal energy. Hence, you can see in this case both the heat as well as the work are taken as positive because the internal energy increases due to both the sources. Due to both the reasons, Q as well as W, internal energy increases. Let me use some symbols like this. Okay, U increases due to both W as well as Q. That is the meaning of this double arrow that I am using here. So how should I write it here? Here in the first case, due to heat, since it is entering, U will be increasing, and due to the work, since it is done by the system, it will cause a decrease in the internal energy. Depending on the magnitude, comparative magnitude of these two factors, there will be either a net increase or net decrease, or internal energy can remain even constant depending on the relative magnitude of the two factors over here. Okay, now third one is quite clear. I am not using any source of heat here. Instead, you can see I have kept a platform here below the cylinder, which is at a lower temperature. You say that this is T low, and let the system is having a temperature TH. So due to temperature difference, heat will flow out. So the heat will be flowing out of the system. Certainly, when heat is flowing out of the system, the internal energy of the system is going to decrease for sure. So I will take Q as negative. Q is negative. But the piston is being pushed down, so it is work done on the system. So work is taken to be again greater than 0, or it is what? Positive. So I can say in this case, due to heat, the internal energy will reduce. Due to the work done on the system, the internal energy will increase. So there is a competition, or you can say there is a comparative thing. Now in the last figure here, you can see again, considering this one as TH, the temperature of the system is higher and the temperature of the platform is lower. There will be always a flow of heat from the system to the surrounding. So there will be Q flowing out, so that is negative. And you can see the work is done by the system, it is expansion, so that will be simply, what is that? That is also negative. So you can see in this case the internal energy of the system will be decreasing due to both the reasons. So it's quite simple to remember the sign conventions. You just remember that whichever process, whether it is heat flow or it is work done, if it causes a reduction in the internal energy of the system, then that thing will be taken as negative. If either of this thing causes an increase in the internal energy of the system, then that quantity should be taken as positive. So it's quite simple and straightforward. We will be using these sign conventions in the coming topics to calculate the net change in internal energy. Remember one more thing, you can see on one side you have got internal energy change, on the other side you have got heat and W. The W here is diathermic work, that you remember. Okay, thank you.